действия частиц и пузырьков, в том числе в процессах флотации. Процесс флотации – это процесс, который широко применяется во многих отраслях промышленности, как для обогащения минералов, минерального сырья, в том числе у нас на предприятии Уралкали, это, в общем, основной производственный процесс, так и для очистки вод и так далее. В общем, повсеместно. И там, конечно, очень главный акт этого флотационного процесса – это именно взаимодействие, я скажу ему, Анатолий, это взаимодействие пузырька и частицы. Ну, значит, вот этой теме и посвящен будет доклад. Мы сотрудничаем с профессором Fornasiero в рамках гранта РНФ с участием ведущих зарубежных ученых. Ну, к сожалению, этот грант вот начался в этом году, в середине года. К сожалению, из-за ковида пока он не смог к нам приехать, но на будущий год и дальше, я надеюсь, он приедет, и он надеется на это. Но это действительно очень известный и активный ученый в этой области. Ну, поскольку у нас сейчас все демонстрируют хирш, то вот я могу сказать, что у него хирш больше 40, то есть он активно публикует, активно работает. И с нами он сотрудничает вместе с ученым из Франции Львом Филипповым, который будет делать днем сегодня, читать днем сегодня лекцию по той же самой проблеме, ну и который тоже ведущий специалист в этой области. Вот лекция профессора Fornasiero будет на английском языке, потому что он не разговаривает по-русски. И вопросы, которые нужно задавать, тоже, пожалуйста, если можно, по-английски, иначе надо будет переводить. Ну, а лекция Льва Филиппова сегодняшняя в 12:40 будет на русском языке, потому что Лев Одиссеевич Филиппов, он окончил МИСИС, ну, и в последние 20 лет он профессор в геологической школе во Франции. Ну, все, я предоставляю слово профессору Fornasiero. Daniel, you can start.
I can start now. Thank you. Yeah, I put on the. So thank you. Thank you, Professor Tatiana Любимова, for inviting me to participate in this PERM Hydrodynamic Forum to present my this presentation on the kinetic of particle bubble interaction and flotation. First, I would like to make a few acknowledgements, financial acknowledgement for the support from the University of South Australia, the Australian Research Council, and the AMARA, so the Australian Mineral Industry Research Association, through the P260 project, which involves several mining companies around the world. And the project started in 1989. And also the contribution of the PhD student who did most of the work in our project. From the beginning, in early 1999, there was David Hewitt, Dong Fu Dai, Brennan Park, and finally Young-Yu Shi. And I would like also to thank and acknowledge the contribution of my dear colleague, Professor John Ralston, who was the director of the INWORK Research Institute. So my talk will be divided in 3 parts. So the first part is the background to the flotation process and the major parameter or variables that affect the flotation recovery. This will be followed by the modeling of this flotation process with a brief description of the various models used in our study, and finally a case study on the flotation of chalcopyrite for further test of this model. So sorry if you have already seen this kind of presentation or slides. As you well know, the principle of flotation rely on the interaction between particle and bubble, and the aim there is to increase as much as possible the grade of the various mineral and in an ore before the eventual further treatment. So for this, the mineral or particle in a size of roughly 10 to 20 micron, 10 to 200 micron, which is the optimum particle size, introduced in the flotation cell as a pulp and are mixed with bubble of size around half a micron, and they interact, and only the hydrophobic particle attached to the bubble and rise at the top of the flotation cell where they are collected in the front. So this technique of separation relies on the difference of hydrophobicity of the surface of the mineral particle. As you can see on the right figure, shows some bubble rising in the pulp, and they have some cold particle are hydrophobic, so that they are attached to the particle surface. You can notice there that the bubble size is not uniform, and also the cold particle are in a cluster, more or less in a cluster. And also I note that the particles are not spherical, they have got some acidity. So all these aspects there can complicate the interpretation of this particle bubble interaction and the explanation and the modeling of the flotation process. In the next slide, I will look at the various variables that affect the flotation process. The first one is flotation time. As you can see on the figure on the right, the recovery of chalcopyrite and pyrite increase with flotation time from 1 minute to 8 minutes of the total flotation time increase. And also as a function of collector concentration, here we have used a xanthate collector, SRPX, and so this reflects more collector is added in the flotation cell, more the surface of the mineral hydrophobic, and so it increases recovery of both mineral increase with flotation time and collector concentration or hydrophobicity. There too, I mean, this figure illustrates that the choice of collector is very important for the selectivity in the separation, and you can see the collector called RBE-CTC is phenocarbamate is more selective against pyrite flotation than the traditional collector. So the second variable, the third variable in the flotation recovery is the particle size, and you can see in these figures that maximum recovery is obtained for a particle size roughly between 60 and 100 micron, and recovery, this was a decrease with decreasing particle size, and also for the coarse particle size. Okay. We note that for the fine particle, even though the recovery is very low at small, it's relatively low at low flotation time, it increases, and after a certain time, like in flotation cell number 12, the recovery reach a level quite similar to the one in intermediate size, but there's no recovery even for long time for the coarse particle more than 300 microns. The next figure, the next variable is particle density, and this is illustrated in this example where that shows that the flotation recovery of mineral for coarse particle decrease with increasing particle density, with silica with a density of 6 to chalcopyrite density of 5, or sorry, 4.2, and galena with density of 7.6. So coarse particle flotation recovery decrease, but the opposite is true for the fine particle recovery, which increase with increasing density of the particle. This is valid at 10 minutes, but also at the beginning of flotation, half a minute. In the next slide, as is the other variable in this recovery of particle is the agitation rate. So agitation rate or turbulence. As you can see in this figure, which is a recovery of chalcopyrite, we see there a large increase in recovery with increasing agitation rate from 150 RPM to 800 or 1000 revolutions per minute. But the opposite seems to be true, or appear to be true for the larger particle of roughly between 100 and 150 micron, which seem to decrease with increasing agitation rate. Now, so in summary, we can say that the flotation recovery rate depend on the hydrophobicity or contact angle of the mineral particle, the particle diameter, the particle density, the agitation rate, turbulence, but also the velocity of the bubble, but also the number and the size of the bubble. So now we go to the next part, which is on the modeling of the flotation process. And there we can see that in this slide, in most of the flotation model, people always divide the process of flotation in 3 consecutive and independent sub-processes, which are the collision first, particle have to collide with the bubble before they can attach to the surface of the bubble. And if the attachment is strong, they can remain on the surface of the bubble. But if the attachment is weak, they are detached from the particle, from the bubble surface. And each of these sub-processes has got an efficiency or probability. First, the collision efficiency, the attachment efficiency, and the detachment efficiency. And the overall particle or collection efficiency, particle bubble collection efficiency or probability, sorry, is the product of these 3 efficiency, collision, attachment, and stability, where ES, stability, is equal to 1 minus the detachment. So now for the collision, if we look at the collision model, most of the collision model assumes that the collision efficiency is proportional to the particle size or diameter and inversely proportional to the bubble diameter, and with proportionality of M and N as the exposant. For example, in the Sutherland collision model, which is a well-known Sutherland collision model, M and N are equal to 1. So all this model, simple model, they assume that fine particle follows the streamlines around the bubble surface, and therefore the interaction is only by intercept. So in this figure on the left, we have compared the several collision models, and all these collision models were established with under various conditions and assumptions, various hydrodynamic conditions, such as the flow regime at the bubble surface. It can be stop flow, potential flow, the mobility of the surface, mobile or immobile, or the collision mechanism, like interception, like we have seen with the Sutherland equation, or gravitation, or in the effect of inertial effect. So, and also the bubble Reynolds number, or bubble size, and the bubble Reynolds number. So all these assumption and aerodynamic condition can explain the large range in collision efficiency observed in this calculation. What we have used a model called General Sutherland GSE or General Sutherland equation, which is derived from the Duquesne model, and we can see that the model reproduced quite satisfactorily the trend of collision efficiency of particle, in this case quartz particle, hydrophobic particle, as a function of particle size. Okay? So this as a function of particle size, and on the right figure we can see that also valid as a function of bubble size, less than 1 millimeter, 0.77, to larger to 1.52 centimeter. So now this is sorry to show you this complicated equation, but this is the Duquesne or General Sutherland equation collision model, which incorporate the efficiency of collision for the Sutherland equation, which is shown the ratio of particle size to bubble size, and also it takes account of the effect of inertial force. And what's the peculiarity of the Duquesne collision model? That it incorporates the positive effect of the aerodynamic pressing force and the negative effect of the centrifugal force, which seems to push away the particle from the bubble surface. So what is the parameter in this equation is theta t, which is the angle of tangency, and this angle of tangency is this one there on the figure at the bottom of the slide, which delineate a region of the bubble surface where the aerodynamic pressing force are more important than the centrifugal force, and for a larger angle of tangency, the opposite is true, where the centrifugal force are more important. Okay, where collision cannot occur after interaction at the surface beyond that angle. We can see that other parameter is k, k3, which is related to the Stock number k, and another parameter in the equation is this beta or beta dimension number, which is proportional to the ratio of the Sutherland collision efficiency to the Stock number, and it is represent the importance of the interceptional effect to the internal contribution to the collision process. So the ratio or the proportion of intersectional effect to collision or to the inertial. So the next model is for the attachment. So the model for attachment efficiency EA. So in the attachment efficiency, people always assume that when the particle collide with a bubble, there is first the process of thinning of the thin film of water between the particle and the bubble. This is followed by rupture if the contact angle is quite high, and after this is followed by the expansion of the contact line triple time. Sorry, the expansion of the free phase line of contact at the particle surface. Okay, so each of these steps have got a time. So the thinning time, the rupture time, and the free phase line of contact time, and the sum of this time corresponds to the induction time. Okay, so the induction time is directly related or inversely proportional to the contact angle. Theta A is an angle. It's called the maximum collision angle, and for it is the maximum collision angle where attachment can occur when the sliding time TSL is equal to the induction time. So Dobby and Finch express an equation where they state that the attachment efficiency EA is the ratio of the area at the bubble surface that correspond to an angle of theta A, this angle of the maximum collision angle, to an angle to the area corresponding to this angle theta T that we have defined. That was the angle of tangency defined in the previous model. This is an equation for attachment efficiency according to the Dobby model. And in this model, when dB, the size of the bubble, is much larger than the size of the particle, like in most flotation system, this maximum collision angle can be related with that equation to the induction time is proportional or inversely proportional. So now, if we look at this figure on the right, we can see that the attachment efficiency, the experimental attachment efficiency represented by the symbol there, is roughly constant with particle size and close to 1 when the contact angle is very high, 74, or relatively high. But this attachment efficiency decrease with decreasing contact angle, as you can see, especially for particle. So the induction time on the figure on the left shows that the induction time derived from this calculation shows that the induction time is roughly constant at small particles less than 10 micron, but it increases with particle size for particle larger than 10 micron. And also that the induction time, like we said before, decreases with increasing contact angle hydrophobicity. So it has been established that the induction time can be related or separate the effect of hydrophobicity can be separate from the effect of particle size with that equation, where A reflects more the hydrophobicity of the particle and the dP with a factor of B, and the size, the effect of the particle size on the attachment or the induction time. And for the particle bubble stability efficiency model, particle detach from the bubble if the sum of the detaching force, like the gravity, capillary pressure, or force, are larger than the sum of the attachment force, and basically the capillary, the static, or the buoyancy force. And so this is here where the gravity force and the and the capillary force or the external acceleration is mainly proportional, dependent on particle size and density, but also for the external acceleration force on the centrifugal acceleration. And this term can be related to the turbulence, energy dissipation, epsilon, and the inversely proportional to the size of the particle bubble aggregate. Schulze, the late Schulze, developed a model for this stability efficiency, and this is a following model, and it is related to the ratio of attachment to detachment. And if detachment is equal to force, stability is equal to 0, but if the attachment force are much larger than detachment force, this stability efficiency is equal to 1. So this is just a representation of these calculations that show the different efficiency and the rate of rotation K. As you can see, with increasing or decreasing contact angle, attachment efficiency decrease. This affects the stability efficiency, which decreases also this characteristic rotation rate constant with a maximum at around 80 to 100 micron. Okay. The same with turbulence. There's more detachment of particle as you increase the turbulence in the system. The last part of the study is for the case study of the flotation of chalcopyrite and particle, flotation of chalcopyrite and particle. The mineral, we use a mixture of 40 gram and 160 gram of chalcopyrite and pyrite. This table at the top shows that the mineral were quite pure, and the mineral were ground, and the D50 size were around 40 micron, quite fine size particle, and this is a particle size distribution. For the flotation, we use this cylindrical Russian flotation cell. It has a height and a diameter similar, 140 millimeter. It has got 4 blades, and the impeller has 6 blades, and there are 4 baffle in the side of the flotation cell. The air gas is introduced at the bottom of the cell through a porous slit, and this produces bubble, and the size was roughly 0.8 of a millimeter, and this was measured independently with UCT, University of Cape Town, bubble size. So gas flow rate was 5 liters per minute. Reagent, we use a xanthate collector to produce optimum flotation condition of and mineral were conditioned at pH 5.1. So this is the experimental result that shows a recovery for chalcopyrite and pyrite that were mixed together, and we can see that the recovery is, as we expected, we have seen before, is optimum for particle of intermediate size, but decrease for fine particle less than 10 micron, and for slightly for larger particle between 120 micron, and the flotation of pyrite is less than the flotation of chalcopyrite as expected. So we use first order rate equation to duplicate the trend of recovery versus flotation time, T, and the 2 parameters in this equation as Rmax, the maximum flotation possible, and K is the flotation rate constant. And from these 2 parameters, we calculate the initial rate constant at T equals 0, K0, which is simply the product of these 2 parameters. And with this information, this fitting, we can calculate the flotation rate constant K0 in minute -1, and there you can see that this rate constant increase with agitation, 650, 800, and 1000 RPM, for the finer size fraction, but for both chalcopyrite and pyrite at the bottom, and the opposite is true, where there is a decrease in a rate constant for the larger particle. Now, we did the fitting, so using all the models that we have shown before, we can calculate this flotation rate constant as a function of frequency of collision, frequency of collision, collision efficiency, attachment efficiency, and stability efficiency, and we obtain this kind of fit there as a function of particle size and agitation, and basically the trend are reproduced with particle size and with agitation rate. The model, the fitting is not perfect, but this is the best fit we have obtained with a flotation model. Now, if we can look on the right, so with that fitting, we have the value of collision efficiency. I just show an example just for chalcopyrite, and we can see there's a decrease at large particle size of this collision efficiency because of the negative effect of the inertial force, and this is even more important as you increase the agitation rate. Attachment efficiency is always larger for chalcopyrite and pyrite because they are more hydrophobic. The collector we use are more selective. Stability efficiency is not very much affected except with the high particle size above 100 micron. So now if we look at the next slide where of the optimum bubble velocity and turbulence energy dissipation rate. That were the two parameters to use to obtain the best fit of the experimental rates constant with the flotation model. We can see that both the bubble velocity and the calculated turbulent energy dissipation increase with impeller speed, in revolution here per second. And if we compare this value of bubble velocity or turbulent energy dissipation with independent measurement of the velocity and energy dissipation in the same flotation cell, the 2.25 liters Russian turbine cell, we can see that the trend, the value are consistent, basically a velocity of 0.3 to 0.6 meter per second, which is roughly the same as the one measured independently with the laser Doppler velocimetry, 0.2 to 0.6. So energy dissipation too is quite low at low impeller speed, 0.04 meter squared per cubic second, and it's roughly the same also there. Maybe there's a slight difference at the high agitation, but this is that with a lot of the probability, this measurement were only done at 60 millimeter from the impeller, distant from the impeller. So obviously, as we decrease the distance, there will be even more turbulence in the system. So in conclusion to my talk, I can say that flotation recovery of rate depend on particle hydrophobicity with the contact angle, the diameter and the diameter of the particle, the bubble numbers, the size and velocity, the agitation rate. The flotation rate constant is a product of particle bubble collision frequency and the efficiency of collision, attachment and stability. And the flotation model that we have used was able to satisfactorily duplicate the trend of flotation rate constant of chakrobite and pyrite as a function of particle size and agitation rate, and the value of bubble velocity and turbulent dissipation rate derived from this calculation are in a reasonable agreement with those measured independently. So this is the end of my talk, and I thank you for listening to that talk.
Okay, thank you very much, Professor Fornasiero.
I think I was right on time, 3 or 4.
Yes, you are quite in time. Вопросы есть?
Sorry?
I have one question.
Yeah.
Okay. Are there any models of such kind taking into account external field as in our case? So we do not have a real model yet for taking into account this external field for every step of flotation process, but for some estimates. Do you know such model? For example, ultrasound is.
Not. I haven't worked or haven't read any paper on how to model the effect of ultrasound. No, I mean, I'm sure there are some models existing which can predict. So do you think there is the effect on the turbulence?
Not only turbulence. I think that also the processes of attachment and collision, of course, but attachment also and detachment.
I mean, it would be good to do, I mean, to see which, I mean, because it's quite complicated, as you can see, there's a lot of variable and parameters that can be modified and changed. So it would be good to see which are the main parameter that affected by this effect of at this stage, no, I can't, because I haven't read any paper on this aspect. I mean, but this can be interesting to do some experiment and try to isolate the more important parameter. I'm sure it's complex, but it can be done.
Okay.
For the future or a collaboration.
Okay. Вопросы еще есть у кого-то? Да, пожалуйста.
Yes, one question. What is the size of bubble
In our experiment,
usual situation?
In flotation cell, industrial flotation is roughly 0.5 of a millimeter. In our case, we measure to be 0.8, so, but it can be 0.8 plus or minus 0.1 to 0.2 of a millimeter. As you can see, there was a large variation in the bubble size.
Okay, but for such rather big size of bubble, I think we need to take into account deformation, effect of deformation of bubbles. Is it important in your model or not?
No, I mean, we haven't taken account deformation bubble, but there was a lot of observation by, I mean, just what I remember, Professor Finch in Canada, or measurement using a video camera, fast video camera, showing that the bubble size is not too much deformed for up to a bubble size of 1 millimeter. So we ignore the deformation of the bubble, but definitely this will have an effect on the velocity of the bubble, rising velocity of the bubble for sure. But we assume that it was constant.
Okay, thanks.
And we assume, like I say, there's so many variations that the bubble size was constant in our calculation. But in the one photograph I've shown earlier, the bubble size was not constant.
Thank you.
Еще есть вопросы? Ну, похоже, вопросов больше нет. So there are no more questions.
Okay,
So thank you very much, Daniel.
Thank you.
And
I'm sorry that I can't share more participation in this conference, but I understand that the language is a problem for me.
Okay, okay. Thank you very much again.
Okay, and good luck with the end of the presentation.
Okay.
Bye.
Так, ну, у нас сейчас утренняя только одна лекция, так что мы переходим к утреннему заседанию непосредственно.